All right, here we go, part 2. So we were looking at those carbon atoms and comparing them based on their difference in electrons and trying to write some definitions. So if we consider something with more electrons than protons, it has a negative charge because it has more negative things than positive things. And we call these anions. I remember this because anions kind of looks like onions, but dyslexic, and onions make you cry and are gross, so it's negative. I don't know. I don't have a good one for that. However, atoms with fewer electrons than protons have a positive charge because they have more positive things. We call these cations. Cats have pos, thus cations are positive. Get it? Because it's a cat and it has paws. Meow. Okay, so the charge for an ion is indicated by writing a superscript to the upper right of the atomic symbol. And so they look like this. What I'd like you guys to do on your student response sheet is identify which of these are cations, which of these are anions, and then identify how many electrons each one gained or lost. Please pause the video to do this, and then we will check in and go over the answers. Did you pause the video? Okay, so the first one we have is sodium. It's positive, so it is a cation, and it lost 1 electron. Oxygen is 2-, which means it's an anion, and it gained 2 electrons. Calcium, 2+, is a cation, and it lost 2 of its electrons. Fluorine, 1-, is an anion, it gained an electron. And last but not least, iron, 3+, is a cation, and it has lost 3 electrons. Very irresponsible of it. So notice that in each of these cases, I'm only talking about electrons. I'm only gaining or losing electrons. I'm not changing protons. I'm not changing neutrons. Charge is all about the electrons. The good news is that the periodic table can be used to predict a lot of charges. So the first family, or the first column on the table, hydrogen, lithium, sodium, and so on, all of those like to lose an electron. And we'll talk about why that is probably later this week or early next week. So lithium, sodium, potassium, rubidium, those all have a 1+ charge. They lost 1 electron. Beryllium, magnesium, calcium, that second column, lose 2 electrons. So they have 2+ and are cations. Boron, aluminum, and so on, those guys usually lose 3 electrons. They have a 3+ charge. And the carbon silicon column can kind of go either way. It could gain 4, could lose 4. So usually it just doesn't do either of those things. Usually it just stays neutral. Nitrogen and phosphorus can go ahead and gain 3 electrons. So nitrogen, phosphorus, arsenic, antimony, bismuth, they all gain 3 electrons. Oxygen, sulfur, selenium, those gain 2 electrons to make them -2 anions. And then fluorine, chlorine, bromine, iodine can gain 1 electron. You'll notice that the last column, helium, neon, argon, they don't gain or lose any electrons. They always stay neutral. They're the noble gases, and they are already perfect in the world of atomic structure, and so they don't need to gain or lose any electrons. You might also notice that hydrogen is listed in 2 places on the table. It's showing it on top of lithium, where we usually see it with a 1+ charge, but sometimes hydrogen acts a little bit more like fluorine and it gains a 1- charge. That's pretty unusual, and we won't really talk about that in this class. In our class, we really are focused on hydrogen losing an electron and having that 1 positive charge. So now I want to give you a little language for talking about the periodic table. Each row on the periodic table is called a period. So rows go across, they're horizontal. And these are arranged by increasing atomic number. So as you add protons, you move across a period. Atomic number tells us our protons. Make sure you remember that. Each column in the periodic table is called a group or a family. Columns go down, so they're vertical. So in this picture, we have each column labeled with a number. So 1, 2, 3, and so on. Members in a group have similar electron structures, and that means they have similar chemical and physical properties. So they react in the same way, so they do the same types of chemistry, and they kind of look the same as well. And so the families become really important when we're studying the periodic table. There are different classes of elements, and they can be classified as metals, and we're pretty familiar with metal. They can be classified as metalloids, and they can be classified as nonmetals. And this really depends on what kind of electron structure they have, what kind of physical properties they have, and what kind of chemical properties they have. So metals make up most of the periodic table, and they always give away their electrons, and they're shown here in blue. Metalloids have properties that fall in between metals and nonmetals. So they sometimes act like metals, they sometimes act like nonmetals, and that actually makes them very unique and powerful. And we use a lot of silicon and germanium in our tech, which is kind of interesting. So those are shown here in this light reddish pink color. And they give away their electrons or they share them. They don't usually gain any electrons. That would be very, very unusual. Nonmetals are shown in green, and nonmetals are really common in living things, and they can share electrons or accept them. So they can take electrons and become negative, or they share their electrons. So carbon, nitrogen, phosphorus, oxygen, sulfur, and hydrogen, those are the main things that make up living things, and all of those are nonmetals. So the nonmetals are really, really important from that perspective. The last thing I want to talk about is valence electrons. And this is a term that we will use because it's very important. Valence electrons are electrons that are in the highest occupied energy level. So that means they're furthest away from the nucleus of the atom. The term valence electrons is better to use than outermost electrons. And there's some intense chemistry reasons for that, so we're not really going to get into it. But we just need to know that the valence electron is in the highest occupied energy level. So why do you think that the definition says highest occupied energy level? Go ahead and on your student response sheet, write a little description of why you think that might be. Okay, so the reason we say highest occupied energy level is because we know that there are many, many energy levels available in atoms. We know that if they interact with light, the photons can cause the electrons to jump up to higher energy levels before they fall back down. And so we don't care about energy levels that are really far away from the atom that are empty. We only care about energy levels that have electrons in them. The rest of the time, the energy levels are totally useless. Okay, so we want to look at some pictures and figure out how many valence electrons each of these have. On your student response sheet, you should answer the question for the next couple of slides and then restart the presentation and go over the answers. So this first element, we don't know what element this atom is, but we can say without a doubt that in the outermost ring, there are only 2 yellow dots. So this has 2 valence electrons. This next one tells us this is hydrogen, and hydrogen only has 1 electron, and that 1 electron also happens to be its valence electron. So we have 1 valence electron for hydrogen. This is oxygen. Oxygen is showing 1, 2, 3, 4, 5, 6 electrons on that outside ring, and so its valence electron number is 6. Aluminum has even more layers, but we only care about that last outside layer, and so the valence number for aluminum is 3. Valence electrons are related to the periodic table because of some of those patterns that we talked about earlier. So you can use the periodic table to predict valence electrons. The first column, the alkali metals, shown here in blue, they all have 1 valence electron. The second column, which are called the alkaline earth metals, beryllium, magnesium, calcium, those all have 2 valence electrons. The transition metals, shown in yellow, are really variable in how they behave, and so we don't really include them in a lot of our generalizations. So we'll skip the transition metals. The third family, boron, aluminum, etc., those have 3 valence electrons. The next family has 4. Nitrogen's family has 5. Oxygen's family has 6. The halogens, fluorine, chlorine, bromine, iodine, those have 7 valence electrons. And then last but not least, the noble gases, shown in red, have 8 valence electrons. And that is a really good thing if you are an atom. You want to have 8 valence electrons. It's very stable. And this valence electron business is going to really start coming in handy when we start talking about bonding at the end of this week. The number of valence electrons that an element has really determine how it's going to bond. And that's why it's important for us to know that. All right, you guys, that is all. So remember, you should be turning in your student response sheet and an upload, whether that's a picture or a scan of your notes that you've taken for this section. This is your only assignment for today, Wednesday, and we will move on to our next piece tomorrow on Thursday. Thanks, you guys. Love you.